Welcome to the Deep Dive. Today we're jumping into something pretty critical, but often invisible, PCIe signal integrity.
Right.
Specifically, how devices actually manage to send data reliably using things like equalization and link tuning.
Yeah.
We've got a bunch of sources here, articles, notes, and the mission is, well, to figure out why just getting data across a wire is so darn hard at high speeds.
It really is surprisingly tricky.
And how PCIe actually solves it. Joining me is our expert guide.
Thanks. It's a fascinating bit of engineering, honestly. Getting those signals across inches of copper through boards, connectors, reliably at, tens of gigabits.
Yeah.
It's a huge challenge. Easy to just assume it works, but underneath, wow, lots of complexity.
Okay, so let's start unpacking. PCIe, I mean, it's everywhere, right? Gaming PCs, servers, AI stuff.
It's the backbone interconnect. Pretty much universal now.
And it just keeps getting faster, doubling seemingly every generation. Gen 1 was, what, 2.5 gigatransfers?
Yeah, 2.5 GTs.
Now Gen 6 is aiming for 64 GTs. That's
Yeah.
quite a leap.
And that massive speed increase, that's where the signal integrity problems really explode. Think about Gen 5, 32 gigatransfers per second.
Okay.
The time for one single bit, the unit interval, or UI, it shrinks down to just 31.25 picoseconds.
Picoseconds, that's hard to even imagine.
It is, and these super short pulses, they're incredibly fragile as they travel through the physical channel.
The PCB traces, connectors.
Exactly. Traces via connecting layers, connectors, cables. All that stuff distorts the signal. It weakens it, smears it out over time.
Yeah.
Makes it really hard for the receiver to tell a 1 from a 0.
Not like the old parallel buses.
Oh, completely different world. Much wider timing margins back then over shorter distances. These speeds are a different beast.
And the PCI SIG, the standards body, their goal is making sure stuff from different companies works together. Interoperability.
Absolutely key. A chip from company A has to talk flawlessly to a board from company B and a card from company C.
Yeah.
You need standardized ways to handle these signal problems.
Gen 6 threw another curveball in there, though, didn't it?
Yeah.
PM4.
Right, PM4 signaling. It doubles the data rate, gets you to 64 GTs, but keeps the actual signaling rate, the symbol rate, at 32 gigabaud. It does that using 4 voltage levels instead of just 2.
So 2 bits per symbol.
Exactly. But the trade-off is huge. Those 4 levels are crammed into the same voltage range that NRZ used for 2.
Meaning the difference between level 1 and level 2, say, is much smaller.
Much, much smaller,
Mhm.
which drastically cuts down your voltage margin, makes the signal way more sensitive to noise and distortion.
So you just had to get better at cleaning up the signal to make TM4 work.
Precisely. PM4 basically demanded more complex equalization, and it made forward error correction, FEC, essential to hit those super low error rates PCIe needs.
So speed demands better EQ, and better EQ enables more speed.
It's that classic engineering cycle, yeah, pushing each other forward.
Okay, so what are these specific problems, the impairments?
Well, the big one, especially at high speed, is insertion loss, or IL. The signal just gets weaker as it travels, and it loses high frequencies more than low frequencies. That leads directly to intersymbol interference, ISI, the sneering effect. One bit bleeds into the next.
Okay.
Then you've got reflections, signals bouncing back when they hit impedance changes, like at a connector or a via.
Like an echo.
Kind of like that, yeah.
Mhm.
Messes things up. Then crosstalk interference leaking between adjacent lanes. And finally, jitter, which is just timing variations, edges arriving too early or too late.
And equalization, EQ, that's the main defense against all this?
It's the primary tool, especially for IL and ISI. The basic idea is pretty neat, actually. You apply a filter that's designed to be the opposite of the channel's distortion.
So if the channel cuts high frequencies, the EQ boosts them.
Exactly. It tries to counteract the channel's effect, sharpen the signal back up, reopen that eye diagram we talked about. And you can do this filtering at the transmitter or the receiver, or usually a bit of both.
And both ends have to agree on how they're doing it, hence the standards.
Precisely. Things like TX presets, the phases in the link training state machine. They're the common language that lets different devices cooperate to get a clean signal.
Let's dig into insertion loss a bit more. Sources say it's enemy number 1, right? Especially as speeds go up.
Definitely the dominant factor for high-speed links. It's just signal power loss measured in dB as it goes through the channel.
Like through PCB traces, connectors.
Yeah, all those physical parts. And the killer is it's frequency dependent. Higher frequencies get attenuated way more than lower frequencies in typical materials like FR4.
So the sharp edges of the signal, the fast transitions carrying the data, they lose the most power.
That's it exactly. And that's what causes ISI. The high frequencies get squashed, the pulse edges get rounded, and the whole thing sprints out in time. Energy from bit n messes up the receiver trying to read bit n plus 1, closes the I diagram.
And this gets worse with faster PCIe generations because the frequencies involved are higher.
That's a crucial point. The critical frequency is often the Nyquist frequency half the data rate. For Gen 3 at 8 GTs, that's 4 gigahertz. For Gen 5 at 32 GTs, it's 16 gigahertz.
Okay.
The loss in standard FR4 PCB material is much higher at 16 gigahertz than 4 gigahertz. So a channel path that worked okay for Gen 3 might have, say, 30 or 40 gigahertz of loss at 16 gigahertz. Utterly unusable for Gen 5 without some serious equalization.
That's why Gen 4, Gen 5, Gen 6 need things like DFE and adaptive CTLE.
They're absolutely mandatory, yes. The channel loss compels their use.
And PCI SIG sets limits, budgets for this loss.
Yeah, they define maximum channel loss budgets. For Gen 5, it's around 36 gigahertz at 16 gigahertz end-to-end. System designers have to meet that, or use things like redrivers or retimers if the path is too long or lossy.
How do engineers actually measure this loss profile?
The standard method uses S parameters, scattering parameters. They describe how the channel behaves across a range of frequencies. For insertion loss, you're mainly looking at SDD21 differential insertion loss.
And the tool for that is?
A vector network analyzer, or VNA. It sweeps signals through the channel and measures what comes out. But there's a catch.
Oh.
You have to connect the VNA using test fixtures and cables, right? And those add their own loss and reflections. So you need to measure the fixtures accurately and then mathematically subtract their effects, de-embed them to see just the channel itself.
Right. Makes sense. And I guess this loss isn't perfectly identical on every single motherboard.
Good point, no. Manufacturing variations in PCB materials, trace etching, they cause variations. Maybe plus minus a 10%, sometimes more, in the loss. Plus, temperature and humidity have small effects.
So designing right to the spec limit is risky.
Very risky. You need margin. Either design the channel to be well below the limit or rely on adaptive equalization in the chips to adjust to the specific channel they see in the final system. Sometimes, even with good design, a channel is just too long and needs a redriver or retimer just to meet the budget.
Okay, channel makes a mess. How does the transmitter chip try to help before the signal even goes out?
That's transmitter equalization, or TXEQ. It's like pre-compensation. The transmitter deliberately shapes or pre-distorts the signal it sends out.
Oh.
It anticipates the channel's filtering effect. The goal is to launch a waveform that, after being distorted by the lossy channel, will arrive at the receiver looking cleaner.
And the main ways are de-emphasis and pre-shoot.
Those are the two key knobs, yeah. De-emphasis, or post-cursor EQ, tackles the fact that transitions lose more power than steady levels. So if you have a string of identical bits, say 111, the transmitter reduces the voltage slightly for the second and third one compared to the first one right after the transition.
So it boosts the transitions relative to the steady bits.
Exactly. Gives those important high frequencies a relative bump. Pre-shoot, or precursor EQ, does the opposite. It slightly increases the voltage of the bit just before a transition. Helps sharpen the edge going into the channel.
How do different vendors agree on these levels?
Through standardized presets. PCI SIG defines a set, typically P0 to P10. P0 is usually no EQ. P10 is strong pre-distortion for very lossy channels. Each preset is a specific defined combination of de-emphasis and pre-shoot.
And the receiver can ask for one.
Yep. During link training, the receiver figures out roughly how much help it needs and requests a specific preset from the transmitter. Like, hey, try sending with P7, ensures baseline interoperability. Under the hood, this is usually done with a simple digital filter, a 3-tap FIR filter. There's a main tap for the current bit, a precursor tap affecting the bit before, and a post-cursor tap affecting the bit after. The preset number just maps to specific coefficient values for these taps.
Simple but effective.
For establishing a baseline, yes. Sometimes the spec allows finer control by requesting specific coefficient values, but presets are the main handshake. And this is evolving too. Gen 6 might use more complex 4-tap TX EQs for PM4.
And these presets are used heavily during that link training process.
Absolutely critical. In the LTSSM's recovery equalization phase, there's a whole dialogue where the receiver evaluates the signal and tells the transmitter which preset to use. It's about getting the signal into a reasonable state before it hits the receiver's own EQ. Compliance testing heavily verifies this. You hook up a scope, tell the transmitter chip to output each preset, capture the waveform, and run analysis tools like SIGTest to check if the voltage levels match the spec precisely.
Okay. TrueX takes the first swing. What about the receiver at the other end?
That's receiver equalization, RxEQ. This happens after the signal has traveled the channel. It's the final cleanup crew. Two main types usually work together: CTLE and DFE.
CTLE first. What's that?
Continuous time linear equalization. It's an analog filter. Think of it like a fancy adjustable treble boost for the signal. It amplifies the higher frequencies more than the lower ones, trying to counteract the channel's insertion loss and flatten the overall frequency response up to that Nyquist frequency. Receivers usually have multiple CTLE settings, different amounts of boost or peaking, often called an EQ gain or index. You pick one based on the channel loss.
Strengths.
Good for smooth, continuous loss, like from long PCB traces. Relatively simple, lower power than DFE. It gives you that initial opening of the eye.
But there's a catch, right? You mentioned limitations.
Yes, a big one. Because it's a linear filter, CTLE amplifies noise and crosstalk right along with the signal at those boosted high frequencies. So if you have a noisy channel, cranking up the CTLE gain might boost the signal, sure, but it boosts the noise even more, potentially making things worse. It's also not great at fixing sharp dips or ripples in the channel response caused by reflections.
Okay, CTLE boosts everything, good and bad. How does DFE avoid that?
Decision feedback equalization. DFE is totally different. It's nonlinear. It doesn't filter the incoming analog signal directly. Instead, it uses the receiver's own past decisions about what the previous bits were.
Wait, after it decided if it was a 1 or 0?
Exactly. It decides bit in. Now it knows, hopefully correctly, whether bit in was a 1 or 0. It then calculates the lingering interference, the tail, that decided bit would cause on the current incoming analog signal, bit in plus 1. It does this using feedback taps with learned coefficients that model the channel's ISI. And then it subtracts that calculated interference from the incoming analog signal before making the decision on bit n plus 1. More taps let it cancel interference from more previous bits.
That's clever. So its advantage is?
The killer advantage. Because it's operating based on decided digital values, DFE does not amplify the incoming analog noise or crosstalk.
Wow. Okay, that's huge.
It's a game changer for noisy channels or channels with lots of reflections, which cause complex, bumpy ISI that CTLE struggles with. DFE cleans that up beautifully.
Sounds amazing. What's the downside?
The main weakness is error propagation. If the receiver makes a mistake, decides that 0 is a 1, that wrong digital value gets fed back. If the DFE tap coefficients are large, that incorrect feedback messes up the subtraction for the next bit, making it more likely to be decided incorrectly, and you can get a burst of errors.
A gene reaction?
Potentially, yes. It's also more complex and consumes more power than CTLE, and standard DFE only cancels post-cursor ISI interference from bits that already happened.
How do they deal with the error propagation risk?
That's where precoding comes in, mandatory from PCI 5.0 onwards. It's a clever mathematical trick applied at the system level. The transmitter scrambles the data in a specific way before sending it. The receiver decodes it after the DFE and the bit decision.
How does that help?
The scrambling to scrambling math is designed so that if a DFE error occurs and propagates for a few bits, the decoding process contains the damage. The output errors after decoding are limited to a short, predictable burst.
And those short bursts can be fixed.
Exactly. By the forward error correction, FEC codes that are also mandatory in newer generations, precoding doesn't make the DFE itself better, but it makes the system much more tolerant of DFE's main weakness. Really neat interplay there.
So CTLE and DFE aren't rivals, they're partners.
Absolutely. Almost always used together. CTLE gives that initial broad boost, fights the main insertion loss, gets the eye somewhat open so the DFE can make reasonably good initial decisions. Then the DFE comes in and does the fine-tuning, surgically removing the complex ISI from reflections without adding noise. So, quick recap. CTLE handles smooth loss, but amps up noise crosstalk. DFE handles reflections post-cursor ISI, doesn't amp noise, but has error propagation, mitigated by precoding. CTLE is simpler, lower power. DFE is complex, higher power. Finding the right balance between them is key, and that's often done by adaptive algorithms inside the chip.
Okay, TXEQ predistorts, RxEQ cleans up with CTLE and DFE. How do the two ends actually agree on all these settings for the specific cable or trace between them?
That's the job of the link training and status state machine, the LTSSM. It's like the conductor of the orchestra. It's hardware logic in the PHY-MAC that takes the link from power on to full speed.
Negotiating everything.
Everything. Speed, lane width, and crucially for us, all the equalization settings. It has to, because neither side knows the channel details initially.
And EQ has its own special phase.
Yes, mostly within the recovery. Equalization substate. The link goes here when trying to reach a higher speed or if it detects problems and needs to reoptimize. It's a multi-phase dance, especially from Gen 3 onwards. Phase 0 is like saying hello, figuring out capabilities, picking a starting TX preset. Phase 1, the downstream receiver tunes the upstream transmitter's TX EQ. Phase 2 reverses that upstream receiver tunes the downstream transmitter's TX EQ, and the upstream receiver tunes its own RX EQ, the CTLE and DFE. Adaptive algorithms often run here. Phase 3 is final checks before going active, L0 state.
Sounds very precise, like step by step.
Extremely precise. Defined down to the bit level by PCI SIG. Any misstep, wrong message, wrong timing, and the training fails. The link won't come up or drops to a lower speed.
Which is why protocol analyzers are so important for debugging this.
Indispensable. You can literally watch the LTSSM progress state by state, see the messages exchanged, and pinpoint exactly where it goes wrong. Gen 6 even allows more time for phases 2 and 3 because tuning PM4 EQ is just harder.
What are they actually sending back and forth? What's the language?
They use special bit patterns called ordered sets. During training, the key ones are training sequences TS1 and TS2, and a new one, TS0, for Gen 6.
And these carry the EQ info.
Yes. Embedded within them are fields for equalization control. Things like recording a specific TX preset, POP10, or sometimes even requesting specific coefficient values for the TX FIR filter tabs. Gen 6's TSCO carries the info needed for its more complex 4-tap EQs and PM4 details.
So this training process has gotten way more complicated over the generations.
Massively. Gen 12 had simple TX stuff. Gen 3 brought in mandatory dynamic TX and RX training. Gen 4 built on that, added FEC. Gen 5 needed DFE and pre-coding negotiation for 36 dB loss. Gen 6 adds PM4, TS0, 4-tap EQ, longer timings, stronger FEC. The LTSSM logic has grown incredibly complex, and it's not just hardware. System firmware, the BIOS or UEFI can influence things too, setting initial parameters, enabling or disabling adaptive features. It's a whole system interaction.
Okay, with all this going on, how do engineers actually know if it's working right in a real system? How do they measure link health?
You need the right tools, specialized test and measurement equipment.
Like what? What's essential?
Top of the list, high bandwidth oscilloscopes. Real-time scopes let you see the waveform live, capture eye diagrams, measure voltages, timing, jitter. Sampling scopes are often used for compliance measurements, essential for checking the transmitter.
Okay, scopes for the TX. What about the receiver?
That's where BERTs come in bit error rate testers. They send known data patterns into the receiver and count the errors coming out. They measure the fundamental BER, receiver sensitivity, and are crucial for stressed eye testing, deliberately degrading the signal to see how much the receiver can handle. Then, for the passive part, the channel itself, you need a VNA, Vector Network Analyzer. Measures those S parameters, insertion loss, return loss, crosstalk, tells you about the physical path.
All right.
And finally, protocol analyzers. They tap into the link and decode the actual PCIe traffic, including those LTSSM training sequences. Absolutely vital for figuring out why training failed or why errors are happening at the protocol level.
So you can't just rely on one tool.
Rarely. A perfect TXX signal doesn't mean the link works if the channel is awful or the RX EQ fails. A noisy signal might look bad on the scope, but maybe the RX EQ cleans it up perfectly, giving a great BER. You need the different perspectives.
And the main metrics are the eye diagram and BER.
Those are the bottom line, yeah. The eye diagram is your visual check. How open is it vertically? That's your noise margin. Eye height. How open horizontally? That's your timing margin against ISI and jitter, eye width. A big, clean, open eye is good.
And MBR.
Bit error rate is the number. Errors divided by total bits. PCIe needs crazy low numbers, like 1 error in a trillion bits, 1012 for older gens. For Gen 6 PAM4, the target before FEC is less than 1 error in a million, 10 to 6 FBER, relying on FEC to clean up the rest. Low BER means the eye is good enough for the receiver. All this gets formally checked during PCI SIG compliance testing, mandatory for the logo. Uses standard test boards, software like SIGTest, very specific procedures, checks TX, RX, and protocol behavior against the specs, but that's just a baseline. Real-world systems need margin beyond basic compliance.
Testing all these combinations and specs sounds overwhelming.
It is. That's why automation software is absolutely critical now. Test equipment vendors provide software that controls the scopes, BERTs, VNAs, manages calibration, runs through all the compliance tests, analyzes the results. Trying to do modern PCIe compliance manually, forget it. Too complex, too slow, too error-prone.
Okay, practical time. Systems built, PCIe link is flaky. doesn't train, runs slow, errors. How do you actually fix it? How do you tune it?
You need a methodical process. First, know your system. What PCIe gen? What's the expected channel loss? What EQ features does your silicon have? Adaptive.dfe. If you can, measure the channel with the VNA. Get real loss data. Then try powering it up. Let the automatic link training, auto-negotiation run. Maybe it just works. If not, grab the protocol analyzer. Watch the LTSSM. Where does it fail? What messages are exchanged? If it trains but is unstable, check signal quality scope for the I, BERT for the BER.
Then you start tweaking.
Then you start guided tuning, based on what you found.
What are common problems and where do you look?
Link won't train at all. Could be huge loss, broken hardware, maybe a fundamental LTSSM protocol mismatch. PA tells you if training got stuck. Scope tells you if there's even a signal. Trains, but slow, like falls back from Gen 5 to Gen 4. Probably channel loss is too high for the target speed, or the EQ couldn't handle it. VNA confirms loss. PA shows the speed negotiation failure. Train's okay, but high BER unstable. That usually points to suboptimal EQ settings, or maybe too much noise or crosstalk that the EQ can't fully fix. BERT measures the errors. Scope might show a marginal I.
What knobs can you actually turn?
Sometimes the BIOS CFI has options. Forcing a speed, maybe selecting a TX preset, though auto-training often overrides this, maybe some lane margining controls, depends on the platform. If you have redrivers, those are usually CTLE-based boosters. They often have configurable gain settings like an EQ index. You'd look at the loss before the redriver, check the datasheet, pick a starting setting, then sweep nearby values while measuring the IBER after the redriver. Placement matters too. Retimers are smarter, they retime the signal too. They usually train automatically, but might have management interfaces like SMBus or I2C for diagnostics, or sometimes vendor-specific tuning overrides. Need the datasheets for those.
So it can get pretty specific to the actual chips involved.
Absolutely. The LTSSM part is standard, but how you configure the details of a specific redriver or retimer, or even access debug features on the main PHY, that's vendor-specific.
And automation helps with the tuning part too.
Hugely. Especially for receiver optimization. Test software can automate setting up stress signals, running loopback modes for BER tests, and doing BER mapping. That's where it sweeps through, say, different CTLE gains and DFE tap settings, measures BER for each combo, and plots a map showing the sweet spot with the lowest BER. It's the only practical way to explore that huge parameter space.
Any final best practices for getting reliable PCIe links?
Yeah, a few key ones. Design with margin, don't aim just for the spec limit, account for variations. Follow strict PCB layout rules, impedance, routing, vias are critical. Use quality components. Let the silicon's adaptive equalization do its job, enable it in LTSSM Phase 2. Verify settings. Test across temperature and voltage. And document your design choices. And remember, while automation is great, sometimes with really tough channels, experienced engineers develop an intuition. They can look at the shape of the eye or the VNA plot and get clues about the main problem, which helps focus the tuning effort. It's often iterative.
Wow. Okay. So we went from the basic problem setting tiny pulses really fast through channel loss, ISI, reflections, to how GX presets give a first push. Then CTLE and DFE do the heavy lifting at the receiver, plus pre-coding for robustness.
Right.
All orchestrated by that complex LTSSM dance and verified with scopes, BERTs, VNAs, and protocol analyzers.
Yeah.
It's a lot.
It is. And mastering this is absolutely key for future I/O. We're seeing PAM4, more EQ taps, more DSP-based approaches, maybe even AML helping optimize things down the road. It's a full system challenge. Materials, chips, software all have to work together.
It really makes you appreciate what's happening when you just, plug in a graphics card.
It does. And maybe a final thought to leave you with. Just consider how much sheer intelligence, sophisticated filters, adaptive algorithms, complex state machines, error correction, pre-coding is crammed into these systems, all just to reliably get ones and zeros across a few inches of copper at blinding speed.
That's a fantastic perspective. Thanks so much for walking us through that complexity.
My pleasure.
And thank you for joining us on this deep dive. Hopefully it shed some light on the hidden magic of PCIe signal integrity. Until next time, keep diving deep into what fascinates you.